For our final example in lesson 3.8, we're going to deal with a classic question, that being, of course, the inverted cone problem. You can see at the top of the screen, geometry definitely comes into play for some of these related rate problems. You're going to need to know the volume of a cone. We've got that right up here. Obviously, that's going to come into play for this problem. 1/3 pi r squared h. Volume of a cylinder. That's the area of the base times the height, pi r squared h. When you deal with the sphere, the volume of a sphere is 4/3 pi r cubed. The surface area of a sphere, 4 pi r squared. But let's go ahead and start looking at this problem in particular. A water tank has the shape of an inverted circular cone. The radius is 2 and the height is 4, and both of those units are in meters. Water is being pumped into the tank, and it's at a rate of 2 cubic meters per minute. With water coming in, the amount of water obviously is increasing, and that's volume. So this rate of change is positive, and it's in regard to volume. dV dt would be a positive 2 cubic meters per minute. Now, as you look at the water filling up, you can see I've already done some preliminary work drawing it. The water is going to take the shape of the container that it's poured into, of course. And we've seen that, for a very long time, since you were children. And, as you look at this water, you will see that there is a circle at the top, much the way that you have a circle at the top of your tank. And we don't know what the radius is at the moment. It's ever changing. The radius of the tank is 2 meters, but the radius of this circle is just r. Obviously, a few seconds later, this water level will rise. That circle will get larger just as well. Same thing with the height, this depth of the water. It's ever increasing as water is being poured in. So we do have a cone for this water. Find the rate that the water is rising. Well, you have h right here. They want you to find dh dt. When the water is 3 meters deep, well, that's your height, and that's only going to be for a fraction of a second. That height will be 3 meters, and then just a second later it will be more, because water is going to continue to get poured in. So this h equals 3m is just going to be used at the very end of our problem, plugging it in for one particular instance. Obviously, as we're looking at the water right here in blue, you can see that our volume, much at the top of our notes that we started with, would be 1/3 pi r squared h. And of course, the volume is changing with respect to time. The amount of water is growing, it's increasing. That r, we said, is increasing as well, and so is h. If I wanted to take a derivative at this very moment, the right-hand side would require us to use the product rule. These are all functions of time. And the problem is I have no information in regard to that radius of the surface circle there, and I don't know a rate of change. So honestly, we don't like seeing 3 variables in this regard. The only way we wouldn't mind it is if we were given a host of information where, we'd be just fine. But look, what I'd like to do is point out that there are some triangles in this problem right here. You can see relatively fast that you've got this right triangle that's really representing the radius of the tank, and then we've got 4 right in here. This is in red, just tracing over that right now. We've got that angle theta down below. Likewise, in the water, we also have this other little right triangle. Here's R, and here's H. And again, you've got theta down here. Well, I hope you see angle, angle. Angle, angle means that we have similar triangles. R over H would be equivalent to 2 over 4. And we could simplify and get R over H is actually equal to 1/2. Now it gets interesting, you see, because I could either multiply both sides by H, which is fine, by the way, we can do that. We'd get R is equal to H over 2. Other kids will say, well, wait a minute, I just want to take this equation and cross multiply, if you would. Get H is equal to 2R. Both of these equations that we're finding are fine. They're valid. They're good. There's just one problem. We're going to really have to pay attention as to which one we're going to use. Our goal is to take one of these equations, substitute it into this volume equation at the top, so that one variable will be dropped out, and then we'll be left with the other variable. Well, I hope you remember that we're asked to find dH dt, and we're given what h is. R is conspicuously absent, so I'm going to take the R equation, R is equal to h over 2, and I'm going to plug that in. You might think, why? Why are you doing that? Well, now I no longer have R in this equation. The only thing I have left are h's. And that's honestly what I'd like to have. Let's clean this up. We will have h squared all over 4 times an h. V then would be 1/12. We'll have a pi, and then we'll have h to the third. What's the benefit? We're down to just 2 variables. I can take derivatives now, and it won't be so bad. In fact, let's just move the screen down a little bit so we can see the top here. We have what dv dt is. I know what h is, and I can find dh dt. Take derivatives, and we can do that. We'll have dv dt. When you bring the 3 down, 3 times 1/12, well, that's going to become 1/4. And we have pi, and here's h squared. That's your derivative. Don't forget the chain rule. dh dt. dv dt was a 2. H itself is momentarily, just for the briefest of moments, a 3. What do we see now? Well, we've got a equation where honestly we can solve. Here's 9 pi all over 4. 3 squared is going to get you your 9. Might think, oh my gosh, how do I get dH dt by itself? How about we multiply both sides by the reciprocal of that fraction? Multiply by 4 over 9 pi. You can see the 4's would cancel out, the 9 pi's would cancel out. dH dt will equal 8 all over 9 pi. Our units were in meters, and it's meters per minute. That is the rate of change for the height, which is the water depth. Now, in class, we also had a follow-up question. We said, what if, for part B, the follow-up question was, and you can see this at the bottom, when h is equal to 3, find out what dr dt is. And at this point, kids could have a terrible sense of foreboding. They can say, this has to be a joke. Oh my gosh, do you really want us to redo this problem? Go through the volume equation, but instead of working with r equals h over 2, in essence work with h is equal to 2r. And that could get very upsetting. Well, thank goodness you don't have to. Here's why. This equation that we did substitute earlier, r equaling h over 2, I could just take the derivatives with respect to time here, and I'd get dr dt The derivative of h is just dh dt, and then of course you've got that 2 in the denominator. That's really a 1/2. And my goodness, we just found dh dt at that instant. dh dt, when h is equal to 3, it was 8 all over 9 pi. So look, all of a sudden you think, hey, I've been working so much with h and dh dt. What if I have to work, in regard to r? You don't have to recreate the wheel. Just find a relationship right here where you can take derivatives and use that rate of change. Obviously, our final answer will be 4 all over 9 pi meters per minute. So that wraps up our related rates. Best of luck to you.